Lesson 11 is key features from graphs of cubic functions, and we've done like key features from quadratic function graphs. So this is kind of like a similar lesson, just a new type of function to analyze. So 11.1 is domain, range, and intercepts, x and y intercepts of cubic functions. So starting at the upper left corner, a cubic function is a function in which the highest degree of the variable is 3. So x to the third power basically, unless you have a different type of variable other than x. So standard form is f of x equals ax cubed plus bx squared plus cx plus d. You don't have to have all four of those terms for it to be a cubic function. You just really need the x to the third term is only like absolute. Okay, these are just a couple of examples of cubic functions. They can look really different depending on what all the coefficients are, but these four are just different examples of what they may look like. You'll notice they're different from quadratics and that, or hopefully maybe notice that they're different and that they're not like a U shape and the ends finish in different directions. So like, this end finishes going up, this one is going down, this one's going down, this one's going up, as opposed to like a quadratic, both sides were going up or both sides were going down. So that is going to impact our end behavior. That's what we do in 11.2. Okay, so example 1, find the key features. So starting with domain. So domain is like basically what possible x values are, and you could tell by looking at the graph. We don't have the function in front of us, but at times you can tell by looking at the function by deciding, what x values can I put in the function that would give me a real number out as opposed to like an imaginary number. But we don't have a function, we just have the graph. So this graph, like it does get pretty steep down here, and it does get pretty steep up here. But those lines are never going to go completely vertical. Otherwise, it would be no longer a function. So if they're not going to ever go completely vertical, that means that we're going to, go left forever, albeit at like a slow rate, and go right forever, also at a slow rate. But the key word is forever. So that means that we're covering all possible x values. So domain is all real numbers, and we're going to write it in interval notation, which would be, between negative infinity and positive infinity. And then between parentheses and brackets, are for when you can include the value. We can't really include infinity, it's not like an actual number. So we would put parentheses around them. Parentheses are used when we cannot include the value. And then range is all the possible like y values, so it's the height of the graph. And we can definitely see, okay, this graph is shooting upward and it's shooting downward. So if it were to continue forever, it would cover every possible y value or every possible output value. So the range is also all real numbers, meaning it goes from negative infinity to positive infinity. It covers every single possible y value. So just as a note, like a reminder to yourself, if you would like, add x next to domain and range, or y next to range, just so you remember which one goes with which point or which coordinate. Okay, so y-intercept, where we're crossing the y-axis. So y-axis is the vertical one. So for where it crosses the y-axis, it crosses right here. So we can list that point. Y-intercepts have an x-coordinate of 0, so this would be 0, negative 2. Since we didn't go left or right at all, we just went down 2. And then x-intercepts, so the x-axis is the horizontal one. We have a couple or a few different x-intercepts here. Which is okay. We have one right here, and right here. So we'll list all those points. Just a heads up, so you can have more than one x-intercept. You should never have more than one y-intercept for a function, because that would make it no longer a function. So we just can't have any like two points that have the same y value but different x values. So you should never have more than one y-intercept. Okay, so for the x-intercepts though, this is negative 2, 0. This is negative 1, 0. 1, 0, and then that's the last one. And then for the zeros of the function, when we've talked about how, zeros and x-intercepts and solutions, all those things are interchangeable, but we just don't really write zeros as points. We just write them as the actual number where it crosses the x-axis. So like for the x-intercept negative 2, 0, the 0 there would just be negative 2. X equals negative 2. And then x equals negative 1 from that second x-intercept. And then x equals 1 from the third one. Okay, and then for where the function is positive, so when it asks where the function is positive, it's sometimes it can get mixed up with like where it's increasing or decreasing. Positive means like the function f of x is greater than 0. So like any possible, sorry, like for greater than 0 is just any positive number. So where is the function positive? So when f of x is greater than 0. So think about how f of x and y are interchangeable. So it's asking like where are the y values of the graph greater than 0, which is anywhere above the x-axis. So it's literally any portion of the graph that is above the x-axis, that's where it would be positive. And then below the x-axis, that's where it would be negative because you have negative values for f of x or for y. Okay, so there's a few different sections for where the function is positive, and you do have to write them in like separate areas. So we zoom in a little bit. So the function is positive right here, and then it's also positive right here. So we'll have to write those. Those are the sections that are above the x-axis. They have positive y values. We have to write them in different parts because they're separate parts of the graph. So for this section, it's between -2 and -1. So that's how we would write our interval. So from -2, and you always put the smaller number on the left, to -1. And then for brackets or parentheses, you have to think about, does it include -2 in the positive or -1? And it doesn't, because so if we think about like this point right here where it like goes up into the positive, that's the point -2, 0. And at that point, f of x is not positive, it's 0, so that's like kind of neutral. So we wouldn't include that or the -1. So when you're talking about where the function is positive or negative, the x-intercepts don't get included because they're not positive or negative there. The value is 0. The f of x value is 0. And then for the second section, so it starts being positive right here, and then it's positive everywhere to the right of that section. So if that's like our starting point, 1 would start at 1, and then everywhere to the right of 1 would be to positive infinity. And then, like I said, we can't include the x-intercepts because they're not positive. They're exactly on the x-axis, so they're at 0. So we put parentheses around 1, and then we can never include infinity. So we'd put parentheses around that as well. And then for where the function is negative, so it's negative down here, and then it's negative or below the x-axis down here. So this first section, or like the far left one, it's kind of like ends being negative at -2. So that's like the higher value. So -2, that's going to be like where my interval ends. And then it's everywhere to the left of -2. So anywhere to the left of a point would be negative infinity, just like every possible value to the left of it. And then parentheses around the negative infinity and parentheses around the -2 as well, because you can't include next intercept because it's neutral. And then the other section, this one right here, looks like I covered up the 1 a little bit, but it is below the x-axis at this -1, and then it stays below and it comes back up at +1. So between -1 and +1, and then same thing, we can't include those numbers because they're not negative there, they're just at 0. Okay, so example 2, same idea, just a different graph. So find the key features starting with domain. So domain, how far is the graph stretching left to right? This one's really similar. So you could see like it's going like left forever, even if it's at a slow rate, because it gets like pretty steep, and then it's going right forever. So we're covering all possible x values. So domain would be between negative infinity and positive infinity. Sometimes my infinities are okay, and sometimes they look like that. And then for the range, it's how far is the graph going up and down. So you can see like this graph is going up forever and down forever. So the range would be the same as the domain. It's all real numbers, so between negative infinity and positive infinity. That's how we write like every number in interval notation, is between negative infinity and positive infinity. And then for the y-intercept, where are we crossing the y-axis? So the y-axis is the vertical one. We cross right here, which is at 0, 0. So 0, 0 is our y-intercept, and then if you have a y-intercept of 0, 0, that's also your x-intercept as well. And that's our only x-intercept. I know it's kind of hard to see in the graph, but it's the only point where it actually touches. It doesn't like stretch along here, it just like slowly moves away from it at first. So our x-intercept is also 0, 0. And then for the zeros, that means, remember, x-intercept and zeros, those go together. So the zeros are just like x equals whatever the x coordinate is from our x-intercepts. Those would be x equals 0. And then for where is the function positive, where is the function negative? So positive is when it is above the x-axis. So like when you have positive y values, basically. And you can even leave yourself a note like positive y values, points that are above the x-axis. So that's this whole section right here. It starts being positive at the origin. So if it starts being positive at the origin, that's the point 0, 0. But I'm really just focusing, because I'm like looking at like, what x value is like kind of the point where it changes from positive to negative. I know they're the same number, but it's important to know that we focus on the x coordinate here when we're looking at where is it positive, where is it negative. So if it's starting to be positive at 0, the first number in the interval notation would be 0, and then it's everywhere to the right of that point. So everywhere to the right would be infinity, and then 0 is neutral. It's not positive or negative, because that point is like exactly on the x-axis. And then infinity means everything to the right of that point, and we can't include infinity, so we'd put parentheses around that also. Sometimes you do use brackets. It really just depends on the context of the problem. Okay, and then for where is a negative, same, like kind of just, it means where are the y values negative? Because this is like where is like the function, and the function is typically like f of x or g of x or whatever it is. And we know that, f of x and y are interchangeable. So it's all just like a different way of asking the same thing, or we can word it a bunch of different ways. Some ways make more sense than others, so it's good to get comfortable with like kind of the different terminology. Okay, so where is a negative? Where are all the y values negative? Where are we below the x-axis? All asking the same thing. So it's negative like on the left side of the graph right here until it hits the origin, and then it flips up to positive. So the way that we would describe that is, it's negative until it gets to x equals 0. So that would be like our ending point for our interval. And then everything to the left. So that would be negative infinity. I think the more infinities I draw, the worse they get. So negative infinity up to 0, parentheses around infinity, and then 0 is neutral, so parentheses around that also. Okay, and then moving down, 11.2 is maximum, minimum, and end behavior of cubics. Sorry, this should be a comma. These are like the same two graphs from the example 1, example 2 from the first section, 11.1. So we're just answering different questions about them. So if you wanted to, if you have the graphs on your notes, you could just add the like different questions or different kind of key features to those same graphs. So example 1, or for both of these, we're going to answer the end behavior and then the maximum minimum and where it's increasing and decreasing. So starting with example 1, the end behavior. Remember, end behavior is just like kind of not a complicated, sometimes it feels complicated. It's just a way of describing like what is the graph doing on its left side and then what is the graph doing on its right side. But sometimes just like the way that we have to write it is the most difficult part. So one thing I want to remind you about end behavior is that, this whole part, like as x approaches negative infinity, f of x approaches, and then the second line, as x approaches infinity, f of x approaches, those are basically like copy and paste. That'll be the same every time you write end behavior. What changes is the very last little blank that I have. So hopefully that helps a little bit. So the first line, as x approaches negative infinity. That means as the x values are getting smaller, that happens on the left side of the graph. So we have to look at what the left side of our graph is doing. It's going down. So if it's going down, that means that f of x is also getting smaller, or slash y is getting smaller. So it's approaching negative infinity. So f of x approaching negative infinity, like this whole thing means the graph is going down because like the f of x values or the y values are just getting smaller. And then for the second line, as x approaches infinity, that means that the x values are getting bigger. So that happens on the right side of our graph. So we look at the right side of our graph, and the right side is finishing upward. So if the right side is finishing upward, that means that f of x is approaching positive infinity. So f of x approaching positive infinity means that the y values slash f of x values are getting bigger, and that happens as the graph goes up. And then the next part, the relative min and the relative max, those are kind of new. So we've done like quadratics that have a true minimum or a true maximum. So for example, if I have a parabola that opens up, the vertex is a minimum because it's a low point. Or if I have a parabola that opens down, the vertex is a maximum because it's a high point. So you can see like from this graph, there's not really like a true minimum or a maximum because like this goes up forever, so there wouldn't be a highest point, it's just infinity. This goes down forever, so there wouldn't be a low point, it's just infinity also. So we have what's called a relative minimum or relative maximum, and that's just a point that is higher than the point surrounding it. So every single part of the graph that is a change of direction is a relative min or a relative max. So I would leave a note that relative min or relative max is a direction change. Or there should always be one where there is a change of direction. Okay, so the first one, relative max. I just want to point out like the parts where it does change direction. So, it changes direction right here and then right here. So it's going from like going up to going down and then going down to going up. So those are our changes in direction. And then to decide if they're max or min, they should be either higher or lower than the points around it. So if I look at the first one on the left, that point is kind of like the top of like a little peak. So it's higher than the point surrounding it. So that would make it a relative max. And then we need to just estimate what that point is and just like emphasis on estimate. It doesn't have to be perfect, it just needs to be close. So for the x coordinate, it's between -1 and -2. So it looks like about halfway in between. So I'm going to estimate it at -1.5. And then for the y coordinate, it's between 0 and 1, but it looks a little bit closer to 1. So I'm going to estimate it at 0.6. And then remember, like a max or a min, same thing with quadratics, it's just the height of the point because it's like, the highest point or the relative highest point. So for the answer part for relative max, I would just put the y coordinate, I would put 0.6, but we will need to use that x coordinate in a second, so we want to know it. And then for this point, it is lower than the point surrounding it. It's like kind of like the bottom of a well or something where it's just, yeah, at the bottom of something, it's lower than the points around it. So that would be a minimum. And then we also need to estimate this point. Also, this one's probably a little bit harder to estimate. For the x coordinate, let's say it's right here, I will estimate that at 0.2. If you did 0.3 or 0.1, that's totally fine. It doesn't have to be perfect. And then for the y coordinate, it's like a little bit below -2, so I'll say -2.1. Same thing if you did like -2.2 or something, like it's just an estimate, it doesn't have to be perfect. And then we just need the height of that point because it's the lowest like relative to the other points around it, so I need that -2.1, and that's my relative minimum. And then for where it's increasing or decreasing, that's like when you follow the graph from left to right, where is it going up and where is it going down? So if I follow the graph from left to right, it's going up first, and then it's going down in between the like max and the min, and then after that it starts going upward. So I just want to describe those like different intervals. I'm going to change one of the colors of them, I think. I don't know if it makes a difference to you guys, but it helps me keep my work more organized. So this middle part is where it's decreasing. So increasing, going up from left to right, increasing right here, up to left to right, from left to right, and then decreasing in here. And then for when we're writing increasing, we're going to put it in interval notation, and because there's two different sections, we have to write two different interval notations. So I'm going to start with the one on the far left. So it's increasing until it hits this like change of direction point right here. And when we're talking left to right, our like boundary lines become the x coordinates because you know left to right, like that's the x value as opposed to the y values up or down. So it's increasing until we get to x equals negative 0.5. So for that one, if it's like until we get to negative 1.5, it would be like 1.5 would be the ending value. And then anything to the left of that is negative infinity. So one of the intervals is going to be between negative infinity and negative 1.5. And then same thing here at negative 1.5, that's where it's changing direction. So it's not increasing, it's just neutral. So that's the first one. And then for the one on the far right, once it hits this point right here, the like change of direction point, that's where it starts increasing again. So that's at x equals 0.2 and anything to the right of it. So it's starting at 0.2 and then anything to the right of it would be infinity. So that's our second increasing interval is between 0.2 and infinity. And then same thing, we can include 0.2, it's neutral. So we would just do parentheses around both. And then for where it's decreasing now, that's the middle section. There is a lot going on this graphic now. I feel like I need to stop and erase some in the middle. But anyways, so for where it's decreasing, that's the purple section in the middle between the two change of direction points. It's going down from left to right. And it's between those 2 points, which the x values of those 2 points are going to be the boundary lines for our interval. So the like starting kind of spot for where it's decreasing is negative 1.5. That's like the far left boundary. And then the far right boundary is this 0.2. So it would be the end of our interval at 0.2. They are both neutral at those points, so we would put parentheses around both. Okay, and then example 2. So first end behavior as x approaches negative infinity. Remember that means the left of the graph. So if I look at the left side of my graph, it finishes going upward. So if it finishes going upward, that means that f of x approaches positive infinity. And then the second line as x approaches infinity, that means the right side of my graph, because the x values are getting bigger, so the right side of my graph goes downward. That means that f of x approaches negative infinity. One thing I want to point out is that when we did quadratics, we talked about how when you write end behavior, they should both be going to the same. So like positive infinity and positive infinity or negative and negative. Cubic functions finish going in a different direction. One side will always go down and one side will always go up, up, down. So when you're writing your end behavior, that's kind of like a good checking point is to make sure one of them is going to negative and one of them is going to positive infinity, because for cubic functions, they'll always finish going in different directions. Okay, so for relative max and relative min, if we look at this graph, there's not really like a true change of direction. So like we're going downward and then it like kind of slows down right there and then it keeps going down though. It doesn't like ever turn and come back up before continuing to go down. It just like flattens out through the middle. So if there's no like true change of direction, there's not going to be like a peak or like a bottom. So there's no relative max or min. So comparing it to like the first example we did, like there were changes of direction. The graph was like going from increasing to decreasing, decreasing to increasing. So every point where it changed direction, like that was a max or a min. This is just like decreasing, 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 decreasing. It doesn't ever increase. It doesn't ever flip back up and come up. So it kind of leads us into increasing and decreasing. So like I said, it's going like left to right, decreasing, decreasing, slows down a bit, but is always like kind of decreasing, except for right here, it's like completely flat. So that's the only like little tricky part. So for where it's increasing, it's not. It's like never increasing at all. So we would just put none or NA or not applicable, I guess. It's never increasing there. And then for like where it's decreasing, it's kind of tricky. So I'll show you a couple of different approaches. It's just a little you have to write it in two parts. Even though like it's like the whole thing looks like it's decreasing, we technically have to write it in two parts because that middle point, it's called an inflection point where it just kind of like flattens out, but it doesn't actually like turn. Um, that breaks up the two intervals. So for increasing, it's never increasing, but for decreasing, there's two parts. So this is at like x equals 0, where it becomes kind of neutral. So if I wanted to write like this first section right here, that's everywhere to the left of x equals 0, with x equals 0 being like the ending point. So that would be from negative infinity to 0. And then parentheses, parentheses, because 0 is neutral. And then we just have to write the second part of it in a different interval. I know it feels kind of like a little tedious or like maybe annoying to do that, but because it's neutral at that middle point, we have to write it in 2. We can't say it's decreasing all the way through. So for the second part, the part that I highlighted in purple, that's starting to be decreasing at 0, and then it's everywhere to the right of it, so it's going to positive infinity. Okay, so just really quick, because this point right here, like you can see it flattens out, it's not decreasing there. So we can't write it as like, negative infinity to infinity because that 0 point is not included. So we have to write it in two sections.